Hello students, today we are going to solve this particular problem. To solve any network problem, we should be having mastery over few tricks. Kirchhoff's laws, for this I have made a special video and you can search for Kirchhoff's laws keyphysics.com. You can search and watch that. Okay. Then voltage distribution trick, for this also I have made one video and with the example you can search this and find. Now with Kirchhoff's laws and voltage distribution trick, any problem, any difficulty level problem can be solved. Okay. Now the thing is, voltage distribution only with Kirchhoff's law any problem can be solved, but a voltage distribution trick makes it a very fast. That's a trick which makes it a very fast. Then there is another simple rule, symmetry rule. Now this particular problem we can solve only using symmetry rule and a voltage distribution trick. Now regarding voltage distribution trick and Kirchhoff's laws, I have made videos. However, on symmetry rule I haven't made a separate video. That's why before coming to this problem, very quickly I'll just explain you the symmetry rule. Well, symmetry rules are of two types. So we can see two symmetries generally in electrical network. That's a current symmetry and a potential symmetry. Current symmetry sometimes is also called mirror symmetry, and potential symmetry is also called folding symmetry. These words are used many times, but I prefer current symmetry and potential symmetry because with the names there's another trick is introduced. Well, suppose we are having a network and if we have to find out the net resistance between P and Q, this is any network, let us say, then if we can find out a line of symmetry, that means if we can find one line, this side will become one mirror image of this side. In that case, currents flowing will be same. So this current, if it is I1 and I2, here this will become I1. Mirror image of I1's image will be I1 and I2 will come like this. I2's image will be I2. And this current will be same as this current will be same as this current. So anyway, current symmetry means currents are same. That's why we call it current symmetry. For potential symmetry, if we are having the lines PQ and about PQ only, if one can be folded on another, if this can exactly fall on this, then we call it a folding symmetry or potential symmetry. The reason being, in a current symmetry, currents are same, and in a potential symmetry, what we can assume is the potential here is same as the potential here, the potential here is same as the potential here. Similarly, potential at any point is the exactly same to the potential of the corresponding point. So what we have discussed just now, we will take up one or two examples so that we'll understand that better. To understand the current symmetry, let's take this electrical network where all are 2 ohms and you have to calculate the equivalent resistance between P and Q. Now see, PQ, against PQ we have to write. If we'll join P and Q, then this is one side it remains and that side is not replicated. That's why clearly it is not potential symmetry, it's a current symmetry. It's not potential symmetry, it's current symmetry or not, let us see. See, if we'll take one line, let me show with a different color. If we take a line like this, then clearly we can see that the image of this is just the image of this 2, 2, 2, 2, 2, 2, 2, 2, and this is 2, 2, 4, 2, 2, 4. So exactly it's a current symmetry. So what we can say is whatever current is flowing, now in between which and which point we need to find out the equivalent resistance. Between those 2 points you can imagine some battery if it's not given in the question also. Okay, so this side is a positive side, this side is a negative side, one battery is connected. Okay, now the thing is if current is flowing like this, it will be divided here, right? So let us say this is I1, this is I2 and this is I3. Now see, since this is a mirror symmetry or the current symmetry, currents will be same. I3 is flowing, these two are in a series, right? If I3 is flowing, I2 is flowing, I1 is flowing, and this is in series of course, so here also I1 only will flow, and this I2 is there, so here also I2 will flow, and here I3 is there, so here also I3 will come. Similarly, whatever current is flowing in this circuit, same current will flow in this. So from this what we can conclude, see I2 is flowing here and I2 only is coming. That means this we can separate, right? This is coming like this and this is going like this, right? So we can say that there is no connection between them. Then this becomes very easy, right? 2 these two became series now. 2 became series and these two are series. So 2 4 ohm 4 ohm, and this is again 4 ohm 4 ohm, and this is 4 ohm, this is 4 ohm. So this circuit can be reduced to 2 ohm, this much entirely, this much I took as this. So 2 ohm, it became 2 ohm, right? Now that is in connection with this 4 ohm series, and this is a 2 to 4 ohm series. So let me write here 4 ohm, and these two are 4 in parallel, so another 2 ohm, and here it is P, here it is Q, right? So these three are in a series now. 4 plus 2, 10 ohm, so that again can be reduced to 10 ohm, 2 ohm, right? This is P, Q. So 10 into 2 by 10 plus 2. R1 R2 by R1 plus R2 is equal to 20 by 12 is equal to, if all are ohm, 5 by 3 ohm. So this way you got how the current symmetry is applied or mirror symmetry is applied. Now we will take for one example for a potential symmetry, and through that we will understand what is a folding symmetry is there and how that is applicable. Now let us take another example to understand the potential symmetry, or sometimes it's called folding symmetry. Now it is one resistance is like this, and all the edges are joined through one resistance. Let us say this point is P and this point is Q, and the question is find the equivalent resistance between P and Q is equal to how much. And let us say all are 2 ohms. So joining PQ, if we draw one line, then this folds, one side folds on other side. If we fold this about this line, and one can be falling on other, exactly, right? And this 2 ohm you can think as this side 1 ohm, this side 1 ohm. This is in series, so you can think that to be in mind 1 ohm 1 ohm, 1 ohm this side, 1 ohm this side. Similarly this 2 ohm also you can think as 1 ohm 1 ohm, right? So it's a folding symmetry. The potential of this point must be equal to the potential of this point. Similarly the potential of this point must be equal to the potential of this point. Now to make a current flow, potential difference between 2 points has to be maintained. Some potential difference, non-zero potential difference must be there. Now between these 2 points, if potential difference is 0, that means potential is same as potential difference 0, no current will flow in this 2 ohm resistance, so this is not there, we can imagine. Similarly, between these two also there is no potential difference, so no current will flow. We can find this out, we can erase it out. Now the circuit became very simple between a PQ. Now see, all these are in a series, 2 ohm 2 ohm 2 ohm, 6 ohm, and here this is a 2 ohm 2 ohm 2 ohm, another 6 ohm in series, and that is in parallel with the 2 ohm. So if I write PQ, P Q, here it is 2 ohm, and one side is 6 ohm, 6 ohm, and this side also is a 6 ohm. Find the equivalent resistance between these three. So 1 by equivalent resistance is equal to 1 by 6 plus 1 by 2 plus 1 by 6 is equal to, take 6 LCM. So 1 plus 3 plus 1 is equal to 5 by 6. Therefore, R equivalent is equal to 6 by 5. And all are in ohm, so 6 by 5 ohm. Clear to everybody?